Yeah, after talking about majority voting in the previous video, this video will cover another fundamental ensemble method called bagging. So bagging is short for Bootstrap Aggregating, so the letters B and then the AGG. That's the inspiration for the name bagging, and it's related to bootstrapping. Bagging was another technique Leo Breiman proposed, and Leo Breiman, you probably recall him from the decision tree lecture. So he was the main person working on CART, the classification and regression trees. And yeah, later in this lecture we will encounter Leo Breiman once more when we will talk about random forests. So yeah, let's start by laying out the algorithm first. It's not very complicated. It looks maybe more complicated than it really is, but you can see it's also only 6 lines here, actually 5 lines if you ignore the blank line here. So it's a very simple approach, and it works as follows. Let's say n is the number of bootstrap samples, so the number of rounds. And then for each round I, we draw a bootstrap sample of size m from the training set. So the training set size is here m. I know it's a little bit weird because we used letters n for the training set size and m for the features, but at some point we are running out of letters. So here n stands for the bootstrap samples, the number of bootstrap samples, and I was using n for the number of bootstrap samples because that's also what we used for the number of classifiers in the previous video when we talked about the Ensemble classifier. So now assume for each bootstrap sample for each bootstrap round you draw a bootstrap sample of size m. So you have n bootstrap samples of size m when you do the bagging, where m is the size of the training set. Okay, and for each bootstrap sample we train a classifier on it. So we train a classifier on this bootstrap sample, and then we do the majority voting again. So fundamentally this is very similar to the Ensemble voting classifier that I showed you in the previous video. The only difference is that instead of fitting each classifier on the training set, we here fit every classifier, the base classifier, on a bootstrap sample of the training set. So I think you have encountered bootstrap samples before in other statistics classes, but if you have not, I just want to recap what bootstrap sampling is. So consider a data set, let's say that's the training data set of size m. Then each bootstrap sample will also have size m, given the previous algorithm, the algorithm on the previous slide. And bootstrap sampling is drawing data points from the data set with replacement. So what will happen is that some of the data points, here I enumerated them from 1 to 10. So m is 10 here, we have 10 data points, and it will also be 10 here. But because it's a sampling with replacement, what will happen is that some records will be duplicated in the bootstrap dataset. So for example, in this case, I have 8 here and 8 duplicated here and here. So each position here is drawn independently from the training set. It's just randomly sampling from the training set with a uniform distribution, so assuming just equal weight for sampling one of the 10 data points. And in each position you do a random sampling. So what will happen is that some of these will be appearing here twice or more, and consequently if some of the data points like this 8 here appears even 3 times, and this is size m, what that means is that some other data points will not appear at all, because otherwise you would exceed the size m. So in this case here these are not included in the bootstrap sample, and we also sometimes call them the OOB samples, the out of bag samples. Out of bag. So they are the ones that are not in the Bootstrap sample at a given round. So here these are the rounds. Round 1, round 2, and round 3. And each round, will be different. So you, in bootstrapping, you will have different training sets, essentially. Given the original training set, you will create new data sets or new training sets. So just going back, you will have n of these bootstrap rounds in backing. And then for each bootstrap sample, you will fit a classifier. So let's take a closer look at the number of examples that are not included in each bootstrap round. So we can take a look at that by looking at the probability of not choosing a particular item for a bootstrap sample. So let's say this is our training set or data set, and we are creating a bootstrap sample, same size, right? And at each position here, so we have, let's say, size m in total. We have then m positions here. And in each position, we draw a random data point with replacement from the training set. So the chance of drawing exactly this one here is 1 over m, because there are m examples in the training set. And we can also, let's say, draw this one or this one. So there's a 1 over m chance that we draw a particular data point. So you have this term 1m here, and then the probability of not choosing a data point for this position from the training set is 1 minus 1m, right? So 1 minus 1 over m is the probability of not choosing one particular data point for this position in the bootstrap sample. But we have m choices here, so we choose m times, so 1, 2, 3, 4, 5 until m. We make this 1 minus 1 over m not choosing choice m times. So the probability of not choosing a particular example in the whole bootstrap set is 1 minus 1 over m to the power of m. That's the probability of not choosing a particular data point like this one for the whole bootstrap sample. Okay, so then what that means is that 0.368 or 36.8% of the bootstrap samples are not chosen in a given bootstrap sample from the training set if m goes to infinity. So if m is really large, if we have a really large data set that we draw from, then 36.8% of the points will not be included in the bootstrap sample. So this is asymptotically, if m goes very large or becomes very large, this is approximately 1 over e, Euler's number. So if the probability of not picking a particular example from the training set for a given bootstrap set is 36.8%, then that means that 36.8% of the data points are not in the bootstrap sample, and consequently 100 minus 36.8%, which is 63.2% of the data points are included in the given bootstrap sample. So 63.2% of the data points are unique in the given bootstrap sample, and the other ones are duplicates. So here at the bottom, I'm just seeing this should actually be m, and this should also be m, because we used m for the dataset size because n was the number of classifiers. It's maybe not the best choice in hindsight. Maybe I should have sticked with n for the dataset size, but anyways. So if m becomes really large, that dataset size becomes very large and approaches even 200, we can see that we approach this 36.2 pretty fast. So I would say 200 is maybe the point where we can say that approximately only 63.2% of the data points in the bootstrap sample are unique. So here's another visual of illustrating the bootstrap sampling in the bagging procedure. So we do the bootstrap sampling multiple rounds. So we said earlier that we do this n rounds if we have n classifiers. And given a data set, let's say we only consider the training indices for the data set. So we have 1 to 7, so a data set of 7 data points. And then this might be a possible first round in bagging. This is the first bootstrap sample. Then we have the second bootstrap sample and so forth. And yeah, we fit a classifier on each bootstrap sample independently. So we have then n classifiers, 1 classifier for each bootstrap round. And what's also very nice about this bagging is that there is no dependency between the bootstrap rounds. So what I mean is you don't have to wait for the second round to finish before you look at the future round, or for the second round you don't have to wait until the first round is finished, until this classifier is finished, with the training, for example. So this is a great opportunity for model parallelism. So you could actually do all the bootstrap samplings in parallel, so you can have this one happening on the first CPU, let's say CPU 1, this one on CPU 2, and so forth. So this is a great case of multiprocessing where you can do all of these in parallel. Now here's a flowchart of the bagging classifier, of how that works. So I try to use the same kind of layout as with a voting classifier to make this relatively similar for seeing how it's different. So here we start also like with a voting classifier with a training set. However, we reuse the training set to make these different bootstrap samples. So we have bootstrap sample 1, 2, up to n, and they're all from the same training set. So we are reusing the training set to make these multiple bootstrap samples. And then for each bootstrap sample, we fit a classifier. So we have now n classifiers. And then each classifier, similar to the voting classifier, the Ensemble classifier we covered in the last video, each of them makes a prediction, and then we use the voting to aggregate these predictions. For example, the majority voting, or we can also do the soft voting. And the majority voting, as we said earlier, is similar to the mode, picking the most frequent class label to come up with a final prediction. So why does bagging work well in practice? So what is the goal behind bagging? Why would we want to use it? Why do we want to use these bootstrap samples? So in order to explain the benefit of bagging, we have to briefly dive into the Bias-Variance Decomposition. So we will revisit the Bias-Variance Decomposition later in the model evaluation lectures, but here it's just like a small teaser. So the Bias-Variance Decomposition is somewhat related to overfitting and underfitting. The concepts are somewhat related, and we will also later discuss in what ways they are related. So you probably have encountered this in previous statistics classes where we had a squared error loss and we decomposed the error, let's say the squared error loss or mean squared error, or let's say mean squared error, where we can compose it into a bias term, a variance term, and a noise term. We will discuss this in more detail later on, and we will also only here in this lecture, in this video, briefly look at the squared error loss for regression, not for classification, because classification is a little bit trickier because we have the 0-1 loss. There are a bunch of papers by Tom Dietrich and I think Pedro Domingos who worked on the 0-1 loss decomposition, but it's a little bit more complicated. So here we are only using the squared error loss, but the same concepts apply, the broader concepts apply also to the 0-1 loss. So let's briefly go over the intuition behind the bias and variance decomposition, ignoring the noise term for now. So there are 4 different combinations. So we have the low variance setting with low bias, which is the ideal scenario. We have the high variance and high bias scenario, which is the worst case scenario. And we have also the other 2 combinations. So the low variance and low bias case here would be a case where a model is precise and accurate. So the Bias-Variance Decomposition is about the loss, but we can also kind of think of it as the model. The more precise and the more accurate the model is, the lower the squared error loss, right? So in this case, this would be, if this is a dart dartboard and we want to hit the center, the bullseye, then low bias and low variance would be a model that makes accurate and precise predictions. In a dartboard, this would be like hitting the center, basically. Okay, so yeah, that is also what I have here on this slide. Then next, let's take a look at the low bias and high variance scenario. So the model is still accurate on, let's say, average, but it's not very precise. So it's scattered. So if we have a dartboard and we throw our darts and in the center is the bullseye, on average, this will be still very accurate. So the average would be in the center. However, it's all scattered around. So each single prediction will not be very precise. There is the case where we have low variance and high bias, and that means that while the predictions are very similar to each other, what happens is that all the predictions are systematically off. So if the bullseye is here, they are all systematically shifted by some degree. So that is also not a good case. And the worst case is if we have a high bias, so all the predictions are systematically off, and they're also highly scattered, so they have a high variance. So this is like the worst case scenario, and this would be, of course, the best case scenario. Here I'm trying to explain the bias variance concepts in relation to, or in a closer relation to, a machine learning problem, or here in this particular case a regression problem. So we are again using a regression example because it's a little bit trickier with a 0-1 loss, and with a regression case it's a little bit easier to draw the problem. So what I have here on the x-axis, that's my feature. So I only have one feature for simplicity, and f of x, this is the true target y, and this is a function, some true function, and we want to use machine learning to approximate this function. So this is the target generating function that we are given. And let's say we have a training data set. Again, this true function is, let's say, some natural phenomenon, something that we actually don't have access to. I'm only drawing it here for reference. And in blue is the actual training data set. And the task is to approximate this unknown function. It is like the typical machine learning or regression case. So in blue is a data set, a training data set. And of course, it's a little bit noisy. So in this particular toy example, I added some Gaussian noise. And the blue dots are our training set. Now suppose I fit a very simple model to this data set. So I have my training set. And the goal is to approximate this underlying true function that we don't have access to. And we fit a simple model. For example, a linear regression model or a decision tree stump. A decision tree stump is a decision tree with only one split. So this is usually called a decision tree stump. It's just a very short decision tree. So decision tree stump means short decision tree. Okay. If we have a very simple decision tree or a linear regression model, we may fit the data like this here. And this would be a case with a high bias. So recall, high bias means that we are systematically off by a certain degree. So here we are off by a certain degree if we have a high bias. Now if we fit a more complicated model, for example an unpruned decision tree, which means a decision tree which is very deep, right? If we have a very deep decision tree, what will happen is that we will fit the training data set perfectly if we don't set a limit to the number of splits. So in this case, we will create a high variance model. Can you think why this model is a very high variance? So the model would be here in blue. So these dots, this would be a decision tree modeling this data set. So why would this be a high variance model? So to explain that, maybe you thought about this a little bit, but to explain that, consider a case where we have multiple training sets, and the training sets are all from this true function. So in fact, what I did is I took this original data set here, in blue, the blue dots, and I divided it into smaller training sets. And this is also usually something we encounter in real life. We have a lot of data available in the world, but usually our training set doesn't include all the data in the world. It's just a smaller set. So here what I did is I divided this set into 3 training sets. The blue dots we worked with before. And if I go back 2 slides, for the blue dots I had this high bias model, and I had this high variance model here. Now what will happen is, if I would use the second training set to fit a decision tree stump, I may find something that is somewhat similar, like this or like this. So this model has some variance because, well, let me use the green one here too, because it will be different every time I fit it. I mean, there will be a small difference based on the different training sets, but it will be not that different. So there's a point where these cross, where we will have exactly 0 variance because they always predict the same thing. So you can think of the variance as a case when we have multiple training sets from the same population. How different are the different predictions if we fit models the same with using the same algorithm on the different training sets? So if I have like these 3 training sets, how much do the predictions differ from each other if we fit a model using the same algorithm? If the predictions don't differ at all, then we have a low variance. If the predictions differ a lot, then we have a high variance. So for example, if we have now also a very complicated decision tree for the orange case here, these predictions will be very different from the blue predictions, right? Using this model. And then for the green one, we again have different predictions. On the next slide I actually have drawn that the actual decision trees fitted on these data sets with a high variance case. However, note that high variance will still result in a good average prediction. So I haven't forgot to do this here, but I will do this definitely for sure for the model evaluation lecture. If we would take the average of these, so the average of these 3 models, we have model 1, 2, and 3, because they are fit on different training sets, then this average prediction will be actually very close to the true function because we are averaging. Whereas if I go back, the high bias models will be still systematically off. They are only good at these different positions where the lines cross with a true function here. In these positions they are actually good models, but everywhere else they're actually pretty terrible with this high bias. Whereas if we have a high variance model, an average over the high variance models, we can still have a good prediction, an accurate prediction. And this is also the idea behind bagging. So in bagging we have like these different training sets, but in bagging the training sets are generated via Bootstrap sampling. So in bagging we have a similar setup to here, where we have multiple high variance models, because bagging usually uses decision trees. So each Bootstrap sample is usually fit to a decision tree. So we have then different decision trees and also the model averaging via the ensemble voting. And through the voting for either class labels or, let's say here in this particular plot, regression outputs, we can actually get a very accurate prediction if we average over them. So the key idea behind bagging is averaging over high variance models. I actually interrupted the recording because there were 2 clarifications I want to make, and it was really bothering me while I was recording the previous slides. So one thing was that I didn't show you the average prediction. So recall this slide where I showed you the 3 decision trees fit on the 3 different training sets. So if we would average them, then we would have the one on the right hand side. So on the right hand side I was averaging the predictions. So what I mean is, let's consider this point here is at minus 15. For the blue one it predicts, I would say it's approximately 220 or something. For the yellow one it predicts 200, and then for the green one it predicts, I don't know what it is, let's say 180. And then I was computing the average, so the average of that, which would be 200, and then I was doing that for every data point here, and then made the plot here on the right hand side. So the plot on the right hand side is showing you the average for this for these 3 regression trees, and that is similar to bagging if you think of each training set as a bootstrap data set, and the bagging then is the averaging in the case of regression, and in the case of classification it would be the majority voting. So we can see here on the right hand side is of course not perfectly approximating the true function, but it comes pretty close. So this function that we have here is actually better than any of these decision trees alone here, right? So this one, the average is actually better at approximating the true function than any of these high variance models. So what we're actually doing is we are lowering the variance here by averaging, which is kind of the concept behind bagging. Yeah, so the second clarification I wanted to make is more related to the decision tree itself. So I was showing you this unpruned decision tree for regression. Was showing you actually multiple ones in the previous plots, but if we have a decision tree, recall actually we can't interpolate values, right? So if we have a decision tree, let's keep it simple and make a short decision tree. And let's say we split on some feature value x1 and say whether it's greater or smaller than 5 centimeters, just to keep it simple. Then on the left hand side, we may have 2 data samples. One, so this is for the y target variable. Let's say this is some value 10 for the first training example, and for the second training example here at this node it's, let's say, 20. And in this one we have maybe for the third training data point 30, and for the fourth one we maybe have 40. Now, if we have an actual data point that is greater than 5 centimeters, then we go to the right hand side, and otherwise we go to the left hand side. Okay, now suppose we have a data point like that is greater than 5 centimeters. What happens is, for this data point, let's call this data point n for new, or let's just say new, and this is, for this data point we have, let's say, I don't know, let's say 7 centimeters or something like that. So we would end up at this node, and then at this node we would be averaging to make the prediction in the regression case. So the prediction would be, I don't have to spell it out, but the prediction would be the average, so 30 plus 40 divided by 2, which is then 35. So the prediction would be 35. Now, if we have a data point that is even larger than 7 centimeters, let's say it's 50 centimeters, it would still go to the right hand side here, right? So in this case, it's also the same prediction. In this case, the prediction would be still 35, because the prediction depends on the labels or targets here at this node. And then let's say only we have a pure node, we only have one training example, we only have this one. Same concept applies. The prediction would always be 30 in this case. So what I mean by that is we can't have these intermediate values. That's actually not correct, because the decision tree can't interpolate. For everything in this range, it would actually be the same value, because, like I just explained, a decision tree can't interpolate. It can only predict the target values that are in the training set, or the average of those, basically. So on the right hand side I was trying to correct the figure if this is an unpruned decision tree. So I have now these flat values here. So it's more like a stepwise function. Unfortunately, I don't know off the top of my head how I can get rid of these connecting lines in matplotlib. I think I have to use the x v-lines function for that, or h-lines actually. No, v-lines. I always confuse those two. To make these steps one by one with a min and max value, and that would be a lot of work. So actually, I think it's h-lines, because these are horizontal lines. Anyway, so I just use the step function here to just make this type of step function, but of course in between these values also don't exist. It's just a step function here. So a decision tree would be plotted just as a step function, and this is not really a decision tree because a decision tree can't interpolate, and this is a little bit misleading here. Yeah, after this little interruption and clarification, let us now finish up this video with a code example, how we can implement the bagging classifier in scikit-learn. So the bagging classifier in scikit-learn can be imported as bagging classifier from the Ensemble submodule, similar to the voting classifier we talked about in the last video. Then these parts I just copied over. So this is exactly the same I had in the last video. This middle chunk is just initializing the dataset. And then for the bagging classifier, what we do is we first initialize a decision tree. So that is the decision tree we want to use for the different Bootstrap samples. We can actually in scikit-learn use something else for the base estimator. That it doesn't have to be a decision tree, but traditionally for that, for bagging, we use decision trees, and we also use unpruned decision trees. So we set the maximum depth to none, which is also the default value. So this will be then an unpruned decision tree. And then we plug in the decision tree into the base estimator of the bagging classifier, and then we have to set the number of estimators. So this is equal to the number of bootstrap rounds that we have. So each decision tree classifier is fit on a different bootstrap sample. Scikit-learn actually lets you disable the bootstrapping of the training set. By default it's true. I'm just showing it here explicitly, but you can actually also set it to false, but then it's not really bagging anymore. However, scikit-learn would allow you, for example, to bootstrap the features, not the training examples, but this would be again not bagging anymore, but the option exists in case you want to experiment with it. Yeah, and also what I mentioned earlier is that, we use a different color now, that we can set the njobs parameter here, and the njobs parameter is for parallelization. By default, if you only have one job, it will only run on one CPU, but I mentioned before, if we have multiple bootstrap samples, let's say bootstrap 1, bootstrap 2, bootstrap 3, and so forth, and each bootstrap sample is fit to a decision tree, let's say tree 1, tree 2, tree 3. We don't have to wait for B2 before we can compute B3, and also for B2 we don't have to wait until B1 is completed. So there is no for loop for computing these in a row. You can actually do all of them at the same time. So you can change this njobs parameter, and then all the decision trees will be fit in parallel, or maybe not all of them, but as many as you have CPUs. So if you have a computer with 4 CPUs and you set njobs to equals to 4, then 4 decision trees will be fit at the same time, for example. So that will accelerate the model fitting for the bagging classifier. And also you could set njobs to -1, then it will just automatically use all the available CPUs on your computer. However, be aware, I know that from some students who have Windows computers. On Windows, on certain computers, it's not always the case. I think it depends on the version of Windows and the version of Python. There are sometimes problems with multiprocessing in Python, so sometimes this code won't work unless you set njobs to equals 1. So on some Windows computers you can only run one job, and otherwise I think what happens is you get an error message or the code crashes. So if you have a problem like that, if you cannot use more than one job because your computer crashes and you're on Windows, it's likely because of the multiprocessing problems in Python on Windows. Okay, so these are the different settings. There's one maybe important setting that I forgot. There's the OOB score that I set to true here. If that's set to true, then in the background, the bagging classifier will also compute the out-of-bag accuracy. So recall when I explained the bootstrapping, when we have our data set here, we create a bootstrap sample like this, let's say this is the same size Bootstrap sample, size M, and this is also size M for the original data set, but because we have some training instances duplicated in the Bootstrap set, we have some of the data points that are not in the Bootstrap sample. So these are our out of back samples, or we call them OOB samples. Yeah, and we looked at this earlier. Only approximately 63% of the data points are unique in the Bootstrap sample, which means that 37% of the data points approximately are in this out of back portion in each round. And then, yeah, the bagging classifier uses these out of back ones to compute the accuracy. So for example, what you could do is you can compute you can fit the decision tree on this Bootstrap sample and then compute the accuracy on this one here, and then you can do that for all of them. So you can do that for each round, for each Bootstrap round, and average over those, for example. And then you get the out of back score. And after training then the bagging classifier, you can actually also show the out of back score. Remember, in scikit-learn, this trailing underscore means that this parameter is only available after model fitting. If you would try to access this attribute before you fit the model, for example, if you would type something like this here, then you would get an error because this is only available after model fitting. So this gives you the accuracy on the out of back samples, and the accuracy in this case is 93%. And on the test set it's 95%. By the way, we also have a validation set here, but we are not using it. You could technically toy around with these different parameters, maybe decrease the number of estimators, or maybe even try the Bootstrap features or something like that and see how that affects the validation accuracy, and then you can recompute the test accuracy at the end. But ideally the test accuracy should only be computed once. For model tuning you should be using the validation set. And also, as a rule of thumb, I recommend just setting the number of estimators really high. Usually the higher the number of estimators, the better the performance. Okay, and that's it for this video. In the next video we will be talking about boosting. Boosting comes in two flavors, or two popular flavors at least. There is adaptive boosting, also known as Adder Boost, and there is gradient boosting, which is nowadays even more popular than Adder boosting. So we will talk about that in the next videos.